Alright. I thought today was Wednesday. I was so happy when I was told it was Thursday. Isn't that a good feeling? Anybody ever do that? Yeah. Alrighty. So, what this is saying is that our function and the binomial that's doing the dividing, those are going to be polynomials. And the guy that's doing the dividing can't be 0, because you can't divide anything by nothing. It's like undefined. Your guy that's doing the dividing is a lower degree than the final Mac Daddy polynomial. And if you get a remainder of 0 anytime with numbers or polynomials, then that means the guy doing the dividing divides evenly into your function. You're not going to do this, but we're preparing your brains for the theory part of calculus. The more you're exposed, the more foreign or the less foreign it's going to seem. Okay? So, one quick aside that I'm just going to touch upon and we're going to move on. We're not going to really have to use this at all that much. Do you remember yesterday we talked about the intermediate value theorem when I said if in an interval, say if this is our x, well, where did that go? All right. Say if this was our x-axis, and in between that interval, do you remember if we said we have a positive y and a negative y, what that means in between that interval? Anybody remember what that said? What did we have in here? It crosses the x-axis, yeah. So that's the intermediate value theorem that we are going to use. There's an example in our notes. This is just an aside of it. And all that this is going to say is if I pick a point in between that interval, and this is some number k, that means that that point, ck, is on our curve and it's continuous. Our curve will be continuous. That's the extension of the intermediate value theorem. This intermediate value theorem is an existence theorem. And it means that a continuous function cannot skip values. It states that if these three conditions that we're going to talk about hold, there is at least one number c in our interval a of b that I drew, so that when I evaluate that function at that random number, we get k. And that's just going to allow us to not have any discontinuity. That's it. Again, exposing you to the theory. All right, so f is continuous on our closed interval a and b. No jumps. That's the first thing. The second thing, when I plug in the endpoints of my interval, their y's are not going to be equal to each other because that could cause a jump. So if I plug in these two and get a y value, they're not going to be equal to each other. And k can be any number between, God bless you, f of a and f of b. Just exposing you to the theory. Now we're going to get to the nitty-gritty. So while you're copying that down, I'm going to start our bonus points. All right. Long division. Only one of these after you're done with that. Mr. D cut these for me and they're like half of it. So for the long division example, who remembers where that binomial goes? Anybody remember, does he go in the house or outside the house? Okay. Huh? No, I should write a list of already. No, because if I wrote Allison, I'd have to give you another one. You did them all too? Okay, remind me, I'm going to come on back. All right. So, who remembers in long division who goes in the house and who goes outside the house? Because I've talked about it. Anybody remember when you do the dividing? What do you think, Bailey? Oh, you did your draw my division house. X minus 4 goes on the outside. Well, I drew a division square. Did you remember synthetic or long division, that any skipped power, you have to hold it with a 0? Did you remember that? If this guy jumped from 5x squared down to negative 12, you would have to hold the x position with a 0. That or with synthetic. All right. I need a 5x squared. I've got an x out front. What do I multiply that x out front by? 5x. You got it. And the x's are in the second column, so that's why I put that 5x over there. So 5x times x is my 5x squared. 5x times negative 4 is a 20x. Do you remember if you add or subtract those lines? One of these is adding and one of these is subtracting. Subtract on this one, yes. So if I subtract, the 5's go to 0, but this is a negative 17 plus 20, or a 3x. Okay. Do you, this 4 hates me and is possessed. Do you remember that 12 would have had to ride the slide down the math lane? Okay. It's, I need a positive 3 up front. What times x gives me a positive 3x? 3, okay. So multiplying, that's a 3x. 3 times negative 4 is a negative 12. Subtracting, I get a remainder of 0.
Right? Is it a positive 12?
So it's a 3 times a negative 4, which is a negative 12, but when I would say negative 12 minus a negative 12, it would make it a plus and go to 0.
Yes. Is it a negative 3x plus?
No. No. I mean, you could if you distributed. I just leave the minus out and do the subtracting and do the...
Oh, okay.
But yeah, if you wanted to rewrite it, absolutely. But that fundamental theorem that we talked about at the beginning says our big honkin' function right there is a result of taking my binomial, my divisor, that was your d of x, times your q of x. We did not have any remainders, so we're not adding it in. But if I FOILed those out, that's what that division algorithm tells us. I hate long division. There's so much room for error. So, synthetic division. Who remembers what goes on the shelf? What do you think, Cohen? It's a positive 4, because if we get a remainder of 0, this fella is a 0 or an x-intercept or a root. And to use that, we would have to solve for x. That's why anytime you pull it out of the parentheses, it switches signs. All right, what's my top row of numbers? Can anybody remember that? What do you think? How about a 5, a negative 17, and a negative 12? All you're doing is taking your coefficients. But a big deal, if somebody's missing, if a power is missing, you got to hold it with a 0. Now, first and third period, we're struggling with the next step. This is tough. This was last year. Sean, computer away, please. Okay, but you need to be writing too. What do I do? You think, Jarrett?
Don't you put a 0 underneath the 5?
You could. So yes, you're not technically wrong. Some teachers teach that way. Did anybody else's teachers teach them to ride the slide down the math lane and start with that? Some people swore they didn't do this last year. They did. You just might not remember it. So you could put a 0, but you need that guy down there. What do I do with the 4 and the 5 to get my next column? What do you think? Yeah, so 4 times 5 is 20. We should get exactly the same numbers that we did previously. 4 times 3 is 12. And you get a 0. Come on, Luke, you're good. So, we've got a squared. Our coefficients are 1 degree less. So, exactly the same as we did. Much easier. you have a good field trip?
Yes, sir.
Good. All right. There's not another practice one, so we're going to do one of your homework problems. You're welcome. So turn to your homework. We're going to do, have a great day, buddy. We're going to do number 3 in our homework together. Just because we don't have a lot of practice. For number 3, I'm going to have you get me started. So I would love for someone to say what goes on the shelf. You don't even have to raise your hand. 3 goes on the shelf because eventually we're going to use this method to find all the roots, all the places these graphs cross the x-axis. No coefficient in front of the third. What am I going to write? 1. All right. Madeline, can you tell me my other numbers up here? We got the 1. Yep. Yep. You got it. Your brain should be thinking when I'm done, I'm going to have a degree 2 polynomial. Alrighty. Writing this slide. 3 times 1 is what, Ethan? A negative 4 plus, remember we're adding, is a plus 3 is a negative 1. Brett, come on in, guys. What am I going to write here? Do you remember what's 3 times negative 1?
Negative 30.
You got it. There's my negative 20, and the first time I worked this, I'm like, good Lord, that's a big number. Don't think you're wrong, because some of these have really big numbers tonight. Did anybody get a negative 60 there?
Yeah.
So, when we don't get a 0, that means that this is not a root. X minus 3 is not one of the 3 binomials that make that guy up. It means that it is not going to cross the x-axis at that point. But our new binomial, 1 degree less, x squared minus 1x minus 20. Does anybody remember what? Yes, dear. Go ahead.
I was gonna ask you what the remainder is.
Well, you don't do it like you did when you were in elementary school. Like that's what we would do. We're not going to do that, but we have to account for it. So that you read my mind. Anybody remember what to do with that negative 54, Elijah? You've got to put it over something. Not 100, but you're right thinking it's going over something. The x minus 3. Yep, you put it over your guy that you divided by. Absolutely. So you all were right. And then listen, do we need to put a plus and a minus, or what could I replace that with? A minus. Yep, you would say minus. Now, in your homework, when you use that factor theorem, if it tells you to write it out as your binomial, your new polynomial, if you write it like this, you're just going to add on your remainder. That when you're not writing it all out, this is how I want it. Okay, did it help doing a second one? Alrighty. Now, one more thing before we go back to our notes, because I need just 3 minutes to get you guys straight. This binomial is different than all of the others because it has a number in front of our x. Can anybody tell me what you would put on the shelf for number 5? Isabel? It was. Because, remember, if this was a true 0 and we were graphing that x-intercept, solving for x, you would get a negative 1/2. Very, very good. So, I helped you with number 5. All right, one more little tidbit of information before I get you your tests back. And that is the remainder and factor theorem. This is going to save you a lot of work. All those binomials we've been using are in the dummy form of x minus k. That number we've been putting on the shelf is k. There is a shortcut, because when we have like polynomials of degree 6, this is going to help you so much. Instead of dividing to find the remainder, if you plug in that k value, or the number you would have put on the shelf, if you plug that into your polynomial, it's going to give you the remainder instead of dividing, because you don't want to divide if you're looking for a remainder of 0. If you could avoid all that work, it'll help you, and that's what we're going to do tomorrow. When they tell you x equals 5, that means it came from the binomial of x minus 5. If I take that number that I would have put on this shelf and plug it in, if my math is correct, I get a remainder of 29.
Please excuse the interruption. Teachers, the students that went on the Holocaust Museum field trip should be back in class now. Thank you.
And tomorrow that's going to help us, because if I say find me all the factors of a polynomial degree 6, you're not going to want to waste your time synthetically dividing to get a remainder of 29 when you can just plug it in and do a check real quick. So if I synthetically divided, it would come out to get a remainder of 29. That's what the remainder and factor theorem do, and that's what it's going to help us get some work done quickly when we have a big, big problem. Okay, so we're going to stop there.